Chapter 19 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 19, Artesian Wells. In our third chapter, we treated of the artificial river, the aqueduct, confined to its course by walls of rock, cement, and metal. The artificial spring, being of at least equal importance as a source of water supply, is also worthy of notice, and the reader will probably be interested to learn some facts concerning the thousands of holes with which the engineer has riddled the upper crusts of the earth in his search for the pure fluid that is so necessary an adjunct to our daily life. The type of well that most often strikes our attention is a hole several feet in diameter lined with brick and cement into which water collects from the surface. Sometimes the dugout is of considerable depth, and as we peer cautiously over the brink, we behold our reflections far below in what appear to be the very abysses of the earth. Such a well is often picturesque and useful, but its day has passed, at any rate in thickly peopled districts. For the chemist with his test tubes and microscope and delicate scales has but too often a doleful tale to tell of the contents of such receptacles. Even if their main supply comes from below, a certain amount of leakage from the surface is inevitable, and the merry microbe soon finds its way in to the condemnation of the whole supply. Sometimes we may see in newly developed building properties, or even in the open country, a small gang of men busy round a steel tripod, raising and lifting a vertical bar on which their attention is centered. If our curiosity is sufficiently aroused to cause a closer inspection, we observe that the bar is slowly but surely eating its way downwards, and that other bars have to be screwed onto it from time to time, these also disappearing in turn. The driving of an artesian well is in progress. The workmen have good reason to suppose that beneath their feet exists a natural reservoir of good water. It may be 100 feet down, or perhaps 1,000, and their duty is to hunt for it until found, when it may gush from the borehole in a fountain, after the manner of a petroleum spouter, or merely rise to a level from which pumps will bring it to the surface. The word artesian is connected with the French province of Artois, where this method of well boring was first practiced in Europe, though known to the Chinese for centuries previously. It may appear at first sight a mystery that in many places a well can be sunk for, say, 50 feet, without yielding any sign of water, and yet deliver a copious amount if the boring be continued for another 500 feet. The riddle is, however, easily solved. Imagine a huge natural basin many miles across, lined all round with clay or some other impermeable stratum. On the top of that a porous layer of chalk, sandstone, or sand. On the top of that again, more clay. Perhaps in the course of centuries the basin is filled up level by deposits of various natures, and finally a town built over it. We may suppose that the area of the basin is not blessed with a heavy rainfall, but that its rim on one or more sides emerges from the earth near a range of hills or even mountains which cause the condensation of the clouds passing over them. The water running down the slopes encounters the basin rim, sinks into it, and finds its way between the watertight strata to the lowest point unoccupied. In course of time the basin lining has sucked in all that it can hold, and overflows at the rim. But the water may become contaminated as it settles into the contents of the basin, and so lose the purity of the hills. The well engineer to whom the geology of a district is known is not disturbed by the apparent scarcity of good water, since he has only to sink a small shaft into the lowest part of the lining to obtain command of its entire contents. If the basin is but partly filled in, so that the center lies lower than the sides, as soon as his drills touch the water-bearing stratum, a fountain shows itself, in obedience to the natural law that water must seek its own level. London lies over such a basin. Hundreds of artesian wells have been driven down to the lining, which through them yields many million gallons a day to the metropolis. The reader will now be able to understand the spouting bores of the most arid tracts of Australia and North Africa. The water that spirits from them in sufficient quantity to keep alive millions of sheep and cattle comes from hills that may be hundreds of miles away, through the natural aqueduct formed by two impervious strata, enclosing one that has the qualities of a sponge. The depth at which a sealed water-bearing stratum exists varies enormously in different localities. Thus the Bourne Well, Lincolnshire, of which an illustration is given, descended but 134 feet before it tapped a source that poured over 5 million gallons a day from its orifice. In the London area, it is necessary to bore from 300 to 500 feet, according to position. And London is well off in this respect as compared with Paris, where the chalk strata lie 6 times as far below the surface. Among the most famous of Parisian wells is that at Grenelle, which was 7 years in the drilling, a 15 months delay being caused by the breakage of the boring rods at a depth of over 1,250 feet. On reaching 1,500 feet without finding water, the engineers would have abandoned the attempt but for the representations of Arago, the famous French astronomer and natural philosopher, who urged them to persevere, with the result that at 1,798 feet the drills suddenly sank into a cavity from which warm water spouted at the rate of 36,000 gallons an hour. In 1855, another well 1,923 feet deep was driven down to the same stratum with a bottom diameter of 28 inches. So great was the pressure that the outflow rose 54 feet into the air to the extent of over 5.5 million gallons a day. Even these were completely eclipsed in profundity by a well near Berlin, which attained a depth of 4,194 feet, piercing a salt deposit 3,900 feet thick. Examples of such wells could be multiplied as the progress of engineering science has made their execution more easy from year to year. Footnote: in Queensland alone, over 800 artesian and sub-artesian, that is, non-flowing wells have been sunk. The bores have an average depth of 1,188 feet, but about 60 range between 3,000 and 5,045 feet. The yield from one bore is 6 million gallons a day, from another 4,500,000 gallons, while 60 more contribute over 1,500,000 gallons. The water from many of the bores has eaten at a course for more than 40 miles, but is now directed by proper channels to the irrigation of thousands of acres of sugar and other tropical and subtropical products. End footnote. In practice, the sinking of artesian bores much resembles the driving of a petroleum well described in a previous chapter. But a water shaft, being intended for a permanency, and having as its object the promotion of health, must be sunk with especial care, and its joints rendered absolutely impervious to impure leakage. By means of artesian bored tube wells, any depth and all sorts of strata can be penetrated. There are various methods of boring, one by connecting lengths of iron rods together to which the various tools are attached, and working the hole up and down until the encountered matter has been pounded into a sludge, which is removed, after the lifting of the rods, by a shell auger or sludge pump. This is called the percussion system. A second is practically that of the American oil seeker. The rods are replaced by a rope, and the weight is concentrated in the drills and their attachments. A third method of percussion employs hollow instead of solid rods for moving the auger. Water is forced through the rods down to the extremity of the perforator, and on its return to the surface brings with it all the debris. Whenever this principle can be used, it proves most expeditious and economical, as the tools need not be removed from the hole for clearing purposes. The fourth is a true drilling method, since the cutter remains in contact with its work all the time. It is effected by means of a ring of diamonds attached to the end of a circular, hollow borer. The diamond drill is a most useful weapon in the hands of the prospector as well as the water engineer, because it enables him to rescue from the depths the solid core that the cutter has gradually absorbed into the hollow rods on its downward path. By inspecting the cores, it is easy to see almost at a glance the nature of the stratum being worked, whereas under the percussion systems the slurry comes up in the form of an unrecognizable sand or sludge. So great is the hardness of the diamond that it can cut thousands of feet through the hardest rock without appreciable damage to itself. Hence the well sinker employs it wherever possible, putting it aside as soon as a soft or friable stratum is met, and returning to his percussion tools. The last two methods can conveniently be used conjointly, as the same set of hollow rods will serve for the two different types of auger. The smallest diamond drills, worked by hand, take cores about an inch in diameter for holes up to 400 feet in depth, while the largest stock size produces a core 16 inches across, weighing upwards of 3 tons, and can be successfully operated at a depth of as much as a mile. Footnote: in Upper Silesia, a bore 6,571 feet was sunk in search of the coal measures. This bore began with a 12-inch diameter, which decreased by stages to 2 3/4 inches. At 6,560 feet, the weight of tubular boring rods was 13.5 tons. 11 feet lower, 4,500 feet of rods broke off and fell to the bottom, whence the engineers were unable to rescue them. This depth is considered to be about the limit of present-day apparatus. End footnote. The engineer lines the bore as it sinks with steel tubes connected by almost flush joints of the same metal until he reaches the chalk. Sometimes, to prevent any possibility of leakage past the tube, he first inserts an outer lining which descends to below the permeable surface strata. The annular space between the two tubes, both of which reach to the surface, is filled in with concrete and made absolutely watertight. On occasions, however, as soon as the inner tube has been firmly embedded, the outer is removed for use in another place. With regard to the quantity of water obtainable by means of artesian bored tube wells, it is unlimited, as the yield can be increased by connecting a series of from the depths of a well, and another, called a crow's foot, that serves the same purpose, and yet a third, styled a bell box, that is let down onto broken rods, passes over a joint and grips it fast when drawn upwards. Without these multifarious devices, many a well would have to be abandoned after it has been sunk for hundreds of feet, and with it a great quantity of pounds, shillings, and pence. Note: the author is indebted to Messrs. C. Isler and Company of Bear Lane, Southwark, for much of the information here given. End of Chapter 19. End of The Romance of Modern Engineering by Archibald Williams.